Okay, and welcome. Thanks for coming. This is the week 10 webinar. This is actually the second to last webinar of the whole class. And it's an important one in terms of useful information that comes up a lot in the real world. So let me tell you the plan of what we're going to be doing. We will start out by, oh wait, sorry. There we go. Start out with Q&A as always, and not just start out, but throughout the whole webinar, I'll answer any questions you might have. And then after that, we will get into scatter plots. So this is chapter 12. So today is all about chapter 12, and chapter 12 is all about linear regression. So we're going to be looking at scatter plots. We're going to be looking at R. And the letter R, you may not be that familiar with what it means in this class, but the word you might have heard before. Have you heard the word correlation before? Yeah, you've probably heard these two things are correlated. And what we're going to be doing is really understanding what that means. Okay, instead of just kind of having a little bit of an idea, we'll really see a line. Okay. Yeah, we will talk about correlation. Well, it's not causation. Okay, that's a big difference, or at least you can't conclude causation from correlation, and that's going to be a biggie. In fact, that's number 6, as you can see. Then we'll get into, I know this sounds like mathematically simple, but R squared. If you take R, you take the correlation, and you square it. It turns out you get something important, and it has kind of almost completely different way of interpreting than just R, and we'll talk about those interpretations. Then we'll look at the regression line. So that is, you might have heard of the line of best fit or the linear regression line, and that's what we're going to be talking about. And then in that, hopefully you might even remember from, way back when you were taking algebra, the equation of a line, you're probably used to it. What's the equation of a line in general? Y equals, who remembers? No, it might have been a while for y'all. Don't remember? Okay, y equals mx plus b. Does that ring a bell? So we're going to be looking at that, and in particular, yeah, a lot of people, it's been a while since you thought about it. We're going to have a slope, and we're going to have a y-intercept. Typically, for reasons are too hard to explain in this class because you need calculus, but often instead of mx plus b, you write it as a plus bx. It's the same thing, just different letters. But we'll be talking about that regression line. We'll talk about, well, what does a slope mean in terms of how do you interpret the slope of a regression line? And also, what does the y-intercept mean? How do you interpret the slope of the y-intercept? That makes sense? Okay, and then, as I heard, avoid using the word causation in anything you talk about with regression analysis if all you've done is regression analysis. So that's a big thing. And I just want to mention, pretty much that's true of just about everything we do in statistics, is that if all of you have is statistics, you can't talk about causation. Okay, you only talk about if one thing happens, what might the other do, or why is it these are two related, that kind of thing. But you don't talk about causation. Causation typically is done using science. Okay, there is sometimes a way of doing checking about causation, and that has to do with control studies, which we talked about in the very first week of class, which is a good chance you all forgot, but we talked about randomized control studies, and then you can talk about causation. Otherwise, definitely not. Okay, then, as I mentioned some weeks back, every week we do a hypothesis test. And it turns out we're going to do a hypothesis test. Anyone know what this letter is right here? It's a Greek letter. It's not P, by the way. Yeah, it's row, like row your boat. It's row. Spelled RHO, by the way, in English, but it's spelled in this letter in in math, in Greek. And rho turns out to be the Greek letter for R. So rho is going to be the population correlation. So we want to do a hypothesis test to see if there is a correlation between two things. And all you have is a sample, which we've seen. That's what we've been doing all quarter, is we just talk about looking at a sample and seeing what we can get from that sample and what you can do as a hypothesis test. So that is the plan. I want to remind you a few things. One is this is week 10. Why is it important that the number 10? Yeah, exam. 10 is an even number. So there's an exam. And the exam covers all chapters 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. But there's a higher focus on 9 and 10 than any of the other chapters. And that's kind of how I've made all of these. It's a focus. There's more points on the most current two chapters. Okay, so there is an exam this week. Make sure you plan for it, get ready for it, and do it well. And practice. Can always do old material stuff, old stuff. And especially chapters, it's chapter 10 and 11 are the most current chapters, because chapter 11 and 12 are the most current chapters. And because of Thanksgiving week, it's been a while since we talked about chapter 11. So make sure that you reread it and maybe practice a little bit before you take the exam. Can always go back and practice the old assignments. Okay, so then the other thing you should be thinking about and working on is the project 2. So at this point, hopefully you've already posted, and I know some of you have, you've already posted your project 2 idea, your H0 and H1, what they are in sentences and also in symbols, and who your client is, how you might be collecting your data, kind of those are the important things. And at this point, hopefully you're actually collecting your data so that you can start writing it pretty soon, because we don't have much time left in the class. It's due a week from Sunday. So we still have some time, but it's not like, a month to do this anymore. Yeah, the final exam will be very similar. Yeah, this is very different than a final exam you've had in other classes. The final exam is very similar to the other exams. In fact, it's exactly the same in points. This is not a course where the final exam has more points than the week 10 exam, for example. They're all equal, the same number of points. Final exam will be the same idea, is that it'll have more focus on chapter 13, a little bit more focus, but then it also will cover all the rest of the chapters. The only difference between the final exam and the rest of the exams is the final exam is due on a Wednesday. Okay, and the reason for it being due on a Wednesday is I need to submit grades. It's one of those requirements. So, I can't make you do things after the course is over. So Wednesday, you take the final, and then I can start grading and stuff and get it all set up. So it's due on Wednesday. It's not due on a Sunday, but you can take it on next Sunday if you wanted. That's fine. Does that hopefully answer your question? Okay, great. Okay, we don't have a lot of people here, but maybe I'll answer the question. So we have at least 3. Things aren't very interesting with just 2 when it comes to regression analysis. So I'll answer it too. So I have a question for you, a survey question. Make it bigger. And that is, including yourself, how many siblings do you have in your family? And how many minutes did you spend exercising? Okay, I should say do. Do you spend exercising in a typical 7 days? Okay, And I want you to put it in the chat box, and I'll just put mine here. So I have, including myself, I'm weird, 4.5 siblings, because I have a half sibling or a step sibling. Okay. I'm also weird on the exercising too. I'm intense. And I would say, let me do the calculation, which is not easy because it's big. Spend about 840 minutes a week exercising, 2 hours a day. Okay. I exercise a lot, more than most, just about anyone I know. But let's look at the others that we have. We also have a 3070, a 370. And we have an only child too. We have one, I'm a 45. Any questions first on the survey? Okay, so one thing to note, by the way, is that this is a very small sample size. In the real world, you would never do something with sample size of 3, but it's all we've got. So it's as good as we can get. Sound good? Okay. The other thing to note is notice this is 2 survey questions. Okay, this would not work for project 2. Why would this not work for project 2? It's 2 quantitative survey questions, but what's wrong with it? Small sample size, but let's say we had a bigger sample size with these 2 questions. Let's say, we were able to ask 31 people. Why wouldn't it work for project 2? I want to emphasize something important. Any ideas? Okay, I don't see y'all jumping in. The reason why it wouldn't work for project 2, they're independent isn't necessarily, actually they're dependent because it's 2 answers for each person, right? So they'd be dependent. The problem is they're not comparable. It doesn't make any sense to say, well, if you look at me, if I take 840 and subtract 4.5, then I get 835.5. That's a meaningless number. Do you see that? Just take how many minutes you exercise minus how many siblings there are is kind of ridiculous. It's meaningless. Do you see that? So this chapter is not about doing a comparison between 2 variables. What this chapter is about is saying, if we know the first variable, will that help us predict the second variable? Does that make sense? So if we know how many siblings someone has, will that give us a good predictor of how much they exercise? Which is not the same thing as saying, is there a difference between the average number of siblings and the average amount you exercise? Totally different. Do you see the difference between the 2 ideas? Okay, so what we can do next is we can put it in a calculator. And what I have done is, there's a couple ways of doing it. First thing, here's the calculator. And notice, where do you think we are in the calculator? Yeah, 24. So one thing to note, we're almost done. After today, we only have one more thing to do in the entire class. And by the way, ANOVA may sound scary, but it's actually one of the easier chapters of the whole class. So the end of the class does not get hard. The hardest part of the end is the project, actually. That's the hardest part because project takes a lot of work. But we're in regression analysis, which is the second to last topic of this whole course, because we only have this week and next week to talk about stuff. Okay, so I'll do it this way first. I'll do it the other way next. So I have 2 ways I made in the calculator. So the first one was 4.5840. 4.5, 840. Let's plot the point. Okay, not that interesting, just one dot. But you can see we have axes. And we can see that 4.5 and then 840 as a dot. And then the next was 3 comma 70. So now I can go 3, and I can go 70, and I can plot points. And what it just did is now there's 2 points. And hopefully you know that if you have 2 points, you could draw a line that connects the 2 points. Do you all agree? For any 2 points, there's always a line that connects them if they're different points. So we have a line, okay? But we actually have 3 points. Can you always connect? Can you always draw a line that goes through 3 points, given any 3 points? Yeah, not usually, actually. Most of the time you can't. And again, I randomly asked you, but I'm pretty sure not going to be able to. 1 comma 45. So let's go 1 comma 45 and plot points. And all of a sudden, we now have 3 points. Do you see this? But a line was drawn. But you notice, or you might notice, that that line doesn't go through the 3 points, does it? Can you kind of see that? Okay, the 3 points, okay, that's called the scatter plot. We actually talked a little bit about that in chapter 2. Was one of the charts that you can do, or graphs, I guess you can do, is a scatter plot. And now we're going to be doing scatter plots. So these 3 points are the scatter plot. And that just means you just plot the points on the XY axes. Okay, where in this case, X was the number of siblings and Y was the number of minutes you exercise. Any questions on that? All right, now you'll notice there's a line here. That line is not just some random line that got drawn by the computer. Do you see at all what that line is doing? See why that line was plotted and say some other line maybe that does that or something out in the other direction? It separates the data, but it's actually a little different than that. It's actually what's called the line of best fit. So if you look at the distance from the point, the vertical distance from the point to the line, and this point to the line, and this point to the line, then it turns out that this line is going to minimize the sum of the squared differences. So it's going to be, in a way, the line that is closest to the points. Okay, whereas if I drew a line that went like that, it would be really, really far from this point over here. Do you see that? And again, with 3 points, you don't see it perfectly, but at least we can quickly draw it. Any questions on that idea? Okay, kind of do this by example. We'll have more examples too. When you have a line, you have an equation. Here's the equation of the line. And that is y equals negative 292.3649 plus 215.5405x. Any questions on that? And that's the equation of a line. The slope would be about 215. I just rounded, made 216, I guess, to round. And the y-intercept would be negative 292. Any questions on that idea? Okay, R is a correlation. And in this case, a correlation is about 0.8-ish, if I round it 1 decimal place. And that's actually not that far from 1. So we can actually say these are strong. This correlation is pretty good. We actually do have a correlation. It does look like as you have more siblings, you tend to exercise more. Okay. Any questions on that idea? Then there's R squared, which I'll talk about in a little bit, but R squared kind of tells you how good a fit the data is. And if you look at the amount of exercising, it's all over the place from this 45 to 840. That's a huge spread of exercising values. Do you see that? But if you look at the kind of the spread near a line, that spread's going to decrease, it turns out. Doesn't work well with 3 points, so we'll do one with more points, and I'll talk about that in more detail. There will be a hypothesis test. I'll get into that in more detail later. And our p-value, by the way, is about 0.368. Even though the correlation was pretty large, why do you think the p-value is pretty big? There's a very important reason that we've dealt with in this entire last 5 weeks or so. Why? Any thoughts on why this is going to be a big p-value, even though the points aren't that far from the line? Yeah, small sample size. When you have a small sample size, good luck having a good p-value. Okay. Any questions on that? So I want to kind of show you kind of this example where we actually plotted a few points. And that was that example. Any questions on this? All right, so let me give you some kind of formal definition-ish of R, somewhat formal. So R is called the correlation. Maybe I'll put that in red because it's that important. So R is the correlation. So correlation is an important word. You've probably heard it before, but didn't really completely understand what it meant. And by the way, you won't completely understand what it means at the end of today either, because you need to have a lot more math to fully understand it, but you can get a better idea than you had before. R is always a number between -1 and 1. Any questions on that? So if you ever see R is -4, you blew it. Okay, that means something went wrong. R is always between -1 and 1. Okay, the sign of R is the same as the sign of the slope. So notice that in our example, our slope, does this have a positive slope or a negative slope, this line? Take a look. Yeah, the slope is positive because it goes up as you go from left to right. And notice that R is also positive, and that'll always be true, is that if your slope of the line is positive, R will be positive also. R is not the slope of the line, but at least it agrees with being positive or negative. And if R is 0, by the way, what will the line look like if R is 0? In one word. Starts with an H. What would the line look like if R is 0? Yeah, the line will be horizontal because whenever you have a slope of 0, you get a horizontal line. Any questions on that idea? Okay, so that just gives you some thoughts or ideas about R. Okay. So if R is close to -1, then the points all belong or all close to being on a negatively sloped line. So if you're like if you're -0.95 or so, that would mean that if you look at the line and you look at the points, the line will go down and the points will be really close to being on the line. Do you see that? Or does that make sense? Okay, if R is close to +1, then the points will be all close to being on the line, but the line will be positively sloped. Any questions on that? If R is close to 0, then the points are all over the place, and then if you didn't see the line, you'd have no good guess of what the line is going to be. Okay. So I like to, kind of a good example of an R is 0 that I like to think, especially since I'm in Tahoe and we have beautiful night skies. And that is, if you think about the night sky and you look at the stars, are the stars near, like close to being on a line, or are they all over the place in the sky? If you look at the stars in the sky at night, especially if you live in Tahoe where you can actually see them. If you live in Los Angeles, you probably can't see any stars. Yeah, they're all over the place. There's no line. And that R, if you looked at let's say, kind of vertical and horizontal area, that R will be really close to zero. Does that make sense? So most of the time when you have R close to zero, there's going to be scattered. Okay, there are other special cases when they're not, and that would be like if they're on a parabola, for example, but that's less common and less important. More important is when they're kind of all over the place. All right, let's see if you can think of a real life example of two survey questions or measurements where R is equal to 1. You think of one. Maybe you can put in the chat box. Let's see if you can give me an example where R is equal to 1. Okay, age of baby, it has to be two questions, right? When you're doing R, there's a x-axis and a y-axis. So there's always going to be two questions. And you want to see if there's a correlation between those two things. So age of babies born in the hospital and something else, for example. Although the age of babies born in the hospital is always 0, because if they're born, they're just born, they're 0. How many hangers do you own? How many shirts do you own? Okay. All right. So that's a good one, except that R won't be 1, R might be 0.9. Right? Because if you have a lot of hangers, there's a good chance you have a lot of shirts. But it's not a perfect line. Okay. Let me give you an example. How about, how tall are you? How are you in inches? And how tall are you in centimeters? Because that actually will be a perfect linear fit, because there's actually an equation. Okay. I don't know the exact equation. I think I did once. That will give, it's a linear equation that goes from inches to centimeters. Does that make sense? So that would be exactly R equals 1. Okay. The only time you get exactly R equals 1 is when there is an equation that tells you, and it's got a positively sloped line. Another would be, say, kind of similar. What's the temperature in Fahrenheit and what's the temperature in Celsius? Right. That has, it's that, what is it? 5 nines x plus 32 or something like that. Okay. Might be minus 32. I have to think about it, but that would be an example where it's a perfectly positively sloped line. Do you see that? Can you think of a survey, two survey questions where R is close to 0? Or two data collections where R is close to 0? Two measurements. Any thoughts? So where might be a real life example of two survey questions or measurements when R is very close to 0? And there's a lot. Those are easier examples, actually. Yeah. So how about, for example, what is the temperature in South Lake Tahoe? And what was the score? Total number of points in the soccer game in New Zealand. Like, if you know what the temperature is in South Lake Tahoe, do you have any idea of, let's say the high school, maybe the biggest high school in New Zealand or something, of how many points that they're going to get in a soccer game? Okay. Yeah, I don't think I can't even imagine there'd be any correlation between those two things. So that would be an R equals 0. Any questions on that? Okay. Now, how about an example where R is close to -1? Can you think of an example where R is close to -1? Thoughts? Okay, even somewhat close. Doesn't have to be exactly like 0.99 or something, but any thoughts? I'm not seeing it. Maybe I'll give you an example. How about how many cigarettes a person smokes each day and how long they live? Okay, so that actually has an R that's not exactly -1, but it's definitely closer to -1 than it is to 0 or 1. Because if you smoke a lot, and hopefully you know this, your chance of living long go down a lot. Does that make sense? Hopefully you've been educated on that, and cigarette smoking is a dangerous thing. Okay, does that mean that everyone who smokes a lot of cigarettes dies young? Yeah, it doesn't mean that because R is not exactly equal to -1. Okay, but there is a correlation, and there's been lots and lots of studies about that to show that there's a correlation, and it's a negative correlation. Any questions on the idea of R so far? Okay, let's do some more. Okay, R squared is the square of R. Okay, so it's not tricky or anything. And I recommend using R squared and turning it into a percent because it'll be easier to understand what it means if you write as a percent. And here's what it is. Okay, so the first thing is you kind of say, well, the variation in the Y variable is pretty big. But if you just look at Y values that have all X values that are almost the same, then the variation, and you can think about it as a standard deviation, is reduced by R squared percent. Okay. So let me kind of explain that in our example. Our example, R squared was about 0.70. Okay. So that means that we can think of R squared as being 70%. Any questions on turning it into a percent? So now what we can say is we can say, well, the variation in the number of minutes per week people exercise is quite large. Some people exercise a whole lot. Some people exercise not so much. But if we just look at cohorts of people who all have the same number of siblings, then on average, the variation of exercise minutes per week goes down by 70%. So what that says is that knowledge of how many siblings someone has is pretty helpful on guessing how much they exercise. Because if you don't know how many siblings they have, it's all over the place. But if you do know how many siblings they have, then the all over the place is 70% less of all over the place. Any questions on this idea? Yeah, I do want to give you a warning that we had a sample size of 3, so it's It's not that great. So does that only have to do with the first variable? Yeah, so it's the idea is the first variable is called the independent variable. The second variable is called the dependent variable. And the idea is you're using the independent variable to make a prediction about the dependent variable. So you're using the first variable to make a prediction about the second variable. Does that make sense? Okay, and that first one, yeah, the first one, and that's a math thing. We always call the x the independent variable and the y the dependent variable. That happened in algebra. You may not remember it, but that was the case. Okay, so when you're doing this whole correlation stuff and linear regression, you have to decide what you want to call the first variable and what you want to call the second variable. And what you do is the first variable should be what you're using to predict the second variable. Okay, so in this example, I'm using siblings to predict the amount of exercise people get. Okay, so we can also say 70% of the variation of exercise minutes per week can be explained by the number of siblings people have in their families. Okay, and 30% is due to other factors. How'd I get that 30%? I did a little basic math. Yeah, 100% minus 70% is 30%. Okay, any questions on this? Okay. So let me do a really important example. And if you're in Tahoe, you know this is the most important example of all data that's ever collected in Tahoe. Do you recognize this picture? Have any of you seen this before? Yeah, that's a measure of lake clarity. So if you're not from Tahoe, I will tell you we have one of the prettiest lakes in the world. And one of the things that makes it so pretty is that it's just very clear. It's beautiful blue. It's not murky. And we want to keep our lake clear. Okay. So one of my favorite stories, and I tell this every year, and this was like decades ago, but one of my statistics students was able to watch this presentation to the President of the United States of America. And that was in the late 1990s. Do you remember who that was? Yeah, President Clinton. Wow, nice. You remembered. Okay, and actually, President Clinton came to Tahoe. And fortunately, this is one of the things I wish is always true, that our president at the time understood statistics really well. Kind of cool. I think all presidents should understand statistics, but maybe I'm biased because I'm a statistics professor. But I think it is important to understand how statistics can be used and when to know that it's done well and not well so that you can use it right. And this was actually shown to President Clinton. And they gave a demonstration of the data of the depth of clarity of Lake Tahoe. And just to give you an idea, what they did is they took a siki dish. I don't know if you've heard of that, but basically it's like a little white plate. And they tie it to a string and they let it go down and down and down and down and down and down until all of a sudden they can't see it because it's too deep. And they measure how deep that is. And I actually talked to UC Davis, actually they're the people who do the data collection and the analysis. And I talked to them, and they don't just do it once a year. Okay, even though it looks like there's only one little Siki dish, for each year. Any guess? And I asked him, any guess on how many times they do it a year? And here's a hint, it made me smile a lot. Flora would not make me smile. This was a bunch of years ago I asked, but I'm sure it's similar. Oh, all right, let me tell you. 31. Why am I smiling? Yeah, yeah, they're actually using, it's like they took my class and they were using what the sample size was needed. So if you take the average of those 31 days that they did the measurements, then you have an approximately normal distribution. And it turns out they only did it on cloudy days. And the reason for that is on a sunny day, you can't see because of the big reflection. But anyway, we talked for a while. And this is the data that collected. And what I did is I cut it off. There's more data now, but this is what was shown to Clinton at the time. And what I did is I looked at these and I eyeballed the data. And this was the year. And what I did, these numbers like 70 is really 1970. Does that make sense? The year 70 doesn't make any sense. It was a year 1970 and the year 1975, etc. These are meters. Here's a question, trick question. If you kind of imagine this line of best fit, does it have a positive slope or a negative slope? Okay, so you didn't hear what I said. This was a trick question. Look at the y-axis, 35, 30, 25, 20, 15. It's upside down. Is that a trick question? So actually it's negative slope. But this is a trick question. And by the way, I would never give you a trick question on an exam or even a homework problem. But I like this example because it's a real world, it's our example in Lake Tahoe. Okay, everybody gets stumped on this one every year. Okay, every quarter. But what I can do is I can take this data and I can put it in the calculator. And I can copy it. Notice I separate by commas. I can also hit new plot so we can start over. And what I did, I did this because someone suggested it, and I'm like, because they said it was just too long to type in all the data, but we can copy and paste all the numbers with commas in the middle. Those are the years, okay, and the after the year 1900 years. And then we can take the meters and put that in the y-axis. And I can click plot points. Okay, and then now, by the way, because I created this, you'll notice now it actually looks like a negative slope line. This one's actually real. Okay, and by the way, this is real data. This is from UC Davis. Okay, this is real data. This is what it looks like. All right. By the way, if you look at this, should you be worried? Let's say this was, the year 2000, and you see the data. Yeah, this would be horrible. Okay, and this is what was happening. What was happening is this. And unfortunately, we saw, okay, that as time was going on, the lake clarity is getting worse and worse and worse. Visually, we can see that. Does that mean every year from one year to the next, it always got worse? No, no. For example, if you look at these 2 years next to each other, it got better. Do you see that? Between, I don't know, that might be 1976 and 1977 or something. Lake clarity got better. But it's not individual 2 years that matter. What matters is the trend. Any questions on that? Okay. And I'll explain what was going on actually in a little bit. There's actually science involved. Okay, we actually can look at R. Oops, too much turning. R is negative 0.85. So we actually have a negative correlation. Unlike with the sibling one, we had a positive correlation. Do you see that? R squared is about 0.72. I like to round to 2 decimal places because that reminds me about percents. The equation of the regression line is y equals 45.6155 and then plus negative or minus 0.2465x. Any questions on that so far? Okay. In our class, we're always going to be doing, well, pretty much most of the time, we'll be doing a two-tailed hypothesis test to see whether there's a correlation or not. Whereas you can also say, is there a negative correlation? Is there a positive correlation? But usually we'll be looking at, is there a correlation? And is the p-value 9.6, by the way, about, or 9.67? Is that the p-value? No, what is the p-value? Yeah, so you really have to always pay attention. The p-value can never be bigger than 1. So if you ever think it's bigger than 1, you are wrong. So then you always move your eyes, and sometimes if you have a smartphone and your screen's too small, you're gonna have to like move the cursor over and look at that e negative 10. So the p-value is actually point, and there'll be 9 zeros before that 9, because you can move it over 10 places. So it's 0.0000000000967. Tiny, tiny, tiny p-value. Any questions on all this, all of our results here before we start interpreting the results? Any questions? Okay, so let's do some interpretation, okay? And what I've done is, let's start out with the line itself. So what I've done is I've created a template, and here's a template I wrote. The slope of a line, you know, is a rise over run. Hopefully you know that from, you know, your basic algebra that you once had. That the slope of a line is rise over run. Do you remember that at one point? Yeah, so the t, so the question is, what about the t value? Yeah, the t value is a test statistic. And that was the same idea as a test statistic. It turns out, and again, the math is way too hard for me to explain why. Turns out that you still use that student's t-test statistic. Turns out it's that. The reason why is like, I couldn't explain to any student on this whole campus because no one would understand. But trust me, that's the math. And it's the same as what you would do, the same variable that you use for, say, difference between two means. Okay. Yeah, and basically, one thing you can do is say, yeah, the t is negative 8.7. That's very, very low. And that's why the p-value is so very small. Any questions on that? Okay, so the slope again is a rise over the run. That happened in basic algebra. So I like to think about it is, how much is y changing when x changes by 1? Any questions on that? Because when you have it as a decimal, then you can always take that decimal and put it over 1, and then you have a fraction. Does that make sense in terms of that math? Any number can be written as a fraction by putting it over 1. Any questions on that idea? Okay. So what that means is that if x is increased by 1 unit, then y is predicted to or tends to increase by the slope units, the number of slope units. Any questions on that idea? All right, so in our example, what was the slope? Let's look at it. What are the slope units? What's the slope? If you look at the screen, the slope is just screaming at you. It's a number. What is the slope? Maybe you can give me 2 decimal places of accuracy is fine. Negative 0.84. No, that's R. The slope is this guy. Because the slope of a line is a number in front of the x. Do you remember that? From basic algebra. So to 2 decimal places, it's negative 0.25. So let me write that down. For our example, the slope is equal to negative 0.25. And now what we can do is we can take that number and interpret it using this if x is increased by 1 unit. What does it mean to increase x by 1 unit for our example, which is our x-axis here? Yeah, wait a year. Okay, so that means if we wait a year, or for every year that passes, so let's write that down. For every year that passes, and then as y is predicted to or tends to, so we can say that on average, the y is a late clarity. That's what y is. Is that clear? Because y is this late clarity in meters. Do you see that? That's the y-axis. The average, then on average, the late clarity has tended to go down by 0.25 meters. Negative means it went down. Any questions on that? Any questions? Does that make sense? Okay, do you remember what the y-intercept means? What it even means to say y-intercept? Yeah, it's the value of y when x is 0. So the y-intercept is the value of y when x equals 0. Okay, the slope, by the way, really always has meaning, and you can always interpret it. The y-intercept sometimes doesn't have any meaning or relevance. Okay, so if x equals 0 has no meaning, then the y-intercept has no meaning. Does that make sense? No relevance. Also, sometimes that y value of the y-intercept has no meaning or no relevance. So those can happen, but sometimes it does have meaning. Okay? Okay, so if it does have meaning, then the y-intercept is the best prediction for y when x equals 0. Here, the y-intercept is about 45.6. Let's go 1 decimal place is good enough. So the y-intercept was 45.6, approximately. Okay. All right. X equals 0. Does that have meaning? With this example, x equals 0. What was that? Do you remember? Yeah, what year is it? Here's the hint. It's not the year 0 in this case. Because this 65 is not the year 65. No, it's not the year 65 either. What was this 65? What did that represent? That's a hint. That'll help you. What year was that? Yeah, that was 1965. So 0 is what year? Any thoughts? 70 was the year 1970. 75 was the year 1975. How about 0? What year would that be? Yeah, 1900. So for this example, the y-intercept is 4.5. The year 1900, does that have meaning? Was there a year 1900, for example? Yeah, there was. But there's not just no data for it, but there's no data anywhere near. We can say, so let me do it in kind of detail. Our best prediction for the Lake Clarity in the year 1900 is a clarity of 45.6 meters. But since none of the data is or anywhere near 1900, which by the way was 0, this is not a good prediction. Any questions on that? Any questions? All right, let's see the following. Now let's suppose that you are, let's say you're presenting. Let's say you're presenting to, the president at the time. I know it's a long time ago. Probably weren't even, some of you weren't even born yet, but that's okay. But let's say you're presenting, and what you want to do is you want to say, well, what's it going to be like in the year 2023? So what is the best prediction for the Lake Clarity in the year 2023? How do we do that? And here's a hint. That's your hint. I just highlighted the regression equation. Any thoughts? Yeah, you're close, but it's a little tricky because remember, this is how many years since 1900? So it's 123. Good, you fixed it. So what we can do is we can take the regression line, we can multiply it by 123. I mean, put x in is 123. And then just to make life easy, I can pop that into the calculator. And it's 15.3 about. The answer is 15.3. Is that okay, by the way, if you live in Tahoe and you care about the environment? Remember, our clarity right now, clarity then was, or at the beginning was like 30. So that means it went down like 50% drop in clarity. Yeah, that's not okay. Okay, that means that things, we got a disaster coming. Okay. All right, so that's something to know. And I'm going to explain that what happened a little bit in the real world and what really happened, which is kind of good. Okay, but here's some words to avoid. Causes. Okay, and I think one of you said that be careful, never say correlation does not give you causation. And then something you may not have thought before, but the word because, if you erase the BE, what are you left with? Cause. So because is also a bad a bad word to use. Okay. So cause, because, don't say if, then it will. Because the word will means that you absolutely know this will happen and you can't know for sure. Do you see that? Better is you use words like predicted that or tends to. Those are much better words with correlation. Any questions on that? And it will take off points if you use anything that relates to the word cause. Any questions on that? So those are mistakes people make. Lots of people make that mistake. All right. We can also say, well, is there a correlation? Maybe our sample size is too small. We didn't have a giant sample size. So what you can do is you can do a hypothesis test. And one of the nice things about chapter 12 is it'll always be exactly the same. H naught will be rho equals 0. If there is no correlation, then rho equals 0. Does that make sense? H1 is rho is not equal to 0, because that means there is a correlation. Any questions on H naught and H1? I want to give you a heads up about the exam. So if and when you have to type in, write down the null and alternative hypothesis, then getting that letter rho is kind of a pain, so I don't require it. You can write RHO, and that's fine. You can also write NOT and then write an equal sign for not equal to, and I accept that. Sound good? Because that's easier to type. Okay, it takes a lot of time and some computer expertise to be able to figure out how to get all this stuff working. Turns out one of the weird things is colon is really hard when you're in the math equation editor. I'm just not even going to go there. So you're allowed to do it using some words instead. Sound good? All right. We had our p-value, which was basically 0, right? As 9 zeros before the next number. Oh, it just happened. There we go. Can you still see it? The H naught, H1? Okay, so I want to make sure because it came off and came back on. Okay. So there is strong and even very strong statistically significant evidence to support the claim that there is a correlation between year and light clarity. Okay. Any questions on that? I do want to let you know that having strong evidence, statistically significant evidence to support the claim there's a correlation, does not mean that there's a strong correlation. Those are different. A strong correlation means that R is really high, like 0.9 something. Okay. So we actually didn't have a 0.9. We don't have a strong correlation. We have strong statistically significant evidence to show there is a correlation, because we had a 0.84 or maybe 0.85, negative 0.85 for R, which is, pretty good correlation, but it's not very strong. Do you see how that is? But our sample size was large enough that we got a very strong statistically significant evidence. Do you see the difference between the two? Any questions on that? Okay. So we have a good correlation, but it's not very strong, but it's maybe strong. R squared is about 0.72. So that means that knowing the year is going to drop the variation in light clarity by 72%. But 28%, if you go 100% minus 72%, that's 28%, really comes from other factors. What are those other factors? Any guesses? This is not a math question, but if you're in Tahoe, you might know. There's another big one. Algae, not quite. That's some, but because the algae actually comes from the year 2, it turns out. Pollution, not quite. It's actually the big factor, should I tell you? Weather. If you have a huge amount of precipitation, you tend to lose light clarity. Okay. And again, you can do another study where you look at how much precipitation happened in that year versus light clarity, and you're also going to find a high correlation. Do you see how that works? Okay, or at least a correlation. And that's the other one. And again, that's not a statistics class thing. That's interesting Tahoe stuff. Okay. Any questions on this? So what do you think they did, by the way? Again, this was around the year 2000. What do you think the president, and by the way, there were senators there too in the meeting. What do you think they did? Given the fact they understood statistics, and unlike today's politics, they didn't just fight all the time. So what do you think they did then? Any thoughts? Okay. Yeah, they actually funded over $100 million for conservation action. Okay. And so what this will tell you, notice in the best prediction was 15.3 meters. Do you think that's light clarity now? Even though that was our best prediction? Okay, the answer is no. And that's because they changed things and they did conservation. Okay. And in fact, I think I have a picture. Here's the newer picture. Okay. What do you notice like between the year 2000 and the year 2020? So the next 20 years. What does it look like going on now? What do you see that happened after they made all this conservation efforts? Yeah, clarity hasn't changed much. I mean, it goes up and down, but it's not like suddenly, it's not continually going bad. Do you see that? So it turns out since the conservation, R is close to 0, it turns out. Okay, so it worked. So this is one of my favorite examples because this is where statistics made a true difference in our town, in our lake. Because by knowing the statistics, they said, we got a problem, let's fix it. And then they fixed it. Okay, it's not perfect. They couldn't get back down to here, but at least it didn't continue going down. Still goes up and down because there's still weather. Weather, we're not, able to, we are changing in the long term, but not in a good way necessarily. So there's weather stuff that's happening. But at least we're not making things worse and worse with all the things we were doing human-wise in Tahoe. Any questions on that? Okay, so here's all the stuff again. Okay, I decided to actually do it. Okay, so here's another example, since we got some time. The good thing about today, about this week, is there's really one thing you have to do. Okay, and they all look similar. I mean, the numbers are different, but they're all going to be similar. There's a bunch of parts. You saw all the different parts we did, but every problem is going to have those parts. Isn't that nice? So let's do another one and we'll have all the same parts, but they'll have different numbers. Okay, so let's look at years of successful education after 10th grade and salary at 30 years old. So in other words, do you think that people who go to school more years after 10th grade, do you think that they make more money? What do you think? By the time they're 30? Yeah. Does that mean that if you spend a lot of years after and go to college and maybe grad school, you will make more money? No, that would be a correlate. That would be an automatic correlation causation. And there may be some causation, but maybe not. Do you see? It might be just that type of person who tends to go to school longer, also tends to do better in jobs. Do you see that? So correlation causation, be careful. Okay, even if it feels like it's causation. It may not be. It may or may not be. Okay. So what I did is we looked at this and we have some data, and I could put the data into the program. I'm just going to refresh. I could also do a new plot, but it do the same thing. And my X values are here. By the way, notice that like this person dropped out of school in 10th grade. Okay. Whereas this person here did 12 years of school after 10th grade. Okay, that'd be like PhD for sure. Okay, or most likely. And then here's salaries. Okay, and I did make these up, by the way. Okay, but you can imagine doing a study like this. And I can hit plot points. Okay, there is a scatter plot. Do you see it? Without even looking at R and R squared and all that, does it look like there's a correlation? Yeah. Do you think it's a positive correlation or a negative correlation? Yeah, it's positive. By the way, do you know how to find the slope if you needed to? If you're just given the line like this? Remember, you do rise over run. So you do the change in y divided by the change in x and two points on the line, and that'll give you the slope. You could get the slope if you know the line. But you can also use what we've got here. Okay, and this gives you all the stuff. So here we have R. Let's start with R. R is about 0.91. So interpret R. So what we can say is, do you remember how to interpret R? When R is 0.91, for example? Is that close to 0? Is it close to 1? Is it close to -1? What's it close to? Yeah, it's close to 1, so we can say there is and it's pretty close to 1. It's over 0.9. Strong linear correlation. Yeah, there's not a perfect number. Typically, like around 0.85-ish, we'll say it's strong. 0.7, we just say correlation, and usually like 0.3, 0.4 and above, that's a weak correlation. And like typically below 0.3 is no correlation or rare, almost no correlation. And that could be negative too, by the way. That makes sense? So there is a strong linear correlation between the number of years of successful education after 10th grade and the salary at 30 years old. Any questions on that? Okay, R squared is about 0.82. Okay. So now we could use that template and we could say that there's a large variation in salaries at 30 years old. But if we look at people or 30-year-olds who, oops, what's that? All had close to the same number of years of successful education after 10th grade, then that variation on average tends to go down or tends to be decreased by 82%. Any questions on that? So that means that it's a good predictor. Does that make sense? So education is a good predictor of salary. Any questions on that? Okay. All right, so let's see if we can make a prediction. If someone has 6 years of education, of successful education after high school, and you kind of think about 2 years, I mean, after 10th grade. So you got 2 years and you got another 4 years of college and maybe you graduate is the idea. So let's see if we can say this. Well, all we have to do is we can take this line here. And hopefully you remember what to do. Hopefully you see that this is really the same as what we did before, but now it's about education and salary. And what do we do to make a prediction for those people who have 6 years of education? What do we do? Yeah, we plug in 6 for x. So we go times 6. Pop in the calculator. And we get about 71 is good enough. Nearest 1,000. So our best prediction for someone with 6 years of successful education after 10th grade is that they will earn a salary of, and again, that was 71 in the dollars, $1,000. Any questions on that? Okay, let's interpret the slope. The slope was about 16.4. So again, we're going to use that same template. So we got to think about if x changes by 1, y tends to change by 16.4. X change by 1 will mean for every additional year of education after 10th grade, on average, the salary tends to go up by $16,400. Any questions? Have I lost you on any of these explanations and interpretations? Okay, let's interpret the y-intercept, or state why it has no practical relevance. Okay, the y-intercept here is negative 27.3. What do you think? Does it have relevance or not? And if it does, what does it mean? So what's your thought? So do you think it has relevance? Yeah, you can't have a salary of negative 27,000. Do you see that? This is a salary, right? This is not what's in your bank account. This is a salary. So since a person cannot have a negative salary, the y-intercept has no relevance. Any questions on that? Okay. So where we are now is the secret word. And the secret word is tens, T-E-N-D-S, because when you're interpreting all these things, you say, as this changes, this other thing tends to go like this. Does that make sense? So that's an important word in regression analysis. It's also one you probably wouldn't just guess if you were to have to guess the secret word. So that's a secret word. And that's pretty much, if you look at it, we've gone through scatter plots, R and R squared, the regression line, which include the slope of y-intercept, and using the regression line, avoid causations, and also a hypothesis test for rho, or for the correlation. So are there any questions about anything? And maybe I'll stop the recording and then you can ask them off recording if you feel more comfortable.